All right. Um, so this is my second video on magnetic fields. I wanted to start by pointing out a few things that I didn't think to say last time. So last time we talked about how magnetic fields cause charged particles that are moving to go through spiral kinds of patterns of motion. And that's true. There's another observation I wanted to make, namely that magnetic forces do no work. So they don't change the energy of a test particle. Hold on, excuse me. The reason that is the following. The formula for work is the integral of the force dotted with the arc length. All right, but the arc length formula is proportional to the velocity. The vector differential there can be written as the integral of f dot v dt, because the path differential is proportional to the velocity vector. And so we have a force, we have a dot product between the force and the velocity vector. But if you look at the formula, the force is always perpendicular to the velocity vector because of the cross product rule. And therefore, this is the angle between these is always going to be 90, and so you get 0 always. So magnetic fields don't, they change the direction of charged particles, make them spiral, but they don't make them speed up or slow down. They don't do work on them. I mean, I'll just say it that way. They don't do work on a particle. Okay. Let's do an example. Let's imagine that we had a charged particle. Let's imagine we have a magnetic field which is going into your eye. Okay. And let's imagine I have a charged particle here, and let's say that the charge is positive. And let's say that it has an initial velocity going this way. Now, I've already claimed that that the motion is going to be circular in nature, but let's see that in a little bit more detail. So in this situation, let's imagine that I have an initial velocity in the, actually, what I'm going to do, because I kind of know where I want this to end up, I'm going to imagine that this is the tangent to a circle. And there are two circles, actually. When Q is positive, V cross B goes down, and so I actually want the lower circle. If Q is, and the particle will just go on a spiral around here. If Q was negative, it would bend the opposite way. And what I'd like to do is come up with an expression for the size of this circle. So to do that, I'm going to identify this velocity vector. It's tangent to the circle, and it goes clockwise. So what I can do is say that that equals the speed, v, times negative theta hat. Because theta hat, where it's measured from the center of the circle. theta hat is always tangent to a circle, because theta hat is the unit vector in the direction of increasing angle. Now, the reason why I would do that, or sorry, further, to simplify that, I'm going to assume that the magnetic field is simply B, some constant magnetic field, times Z hat. So we'll say the Z direction is coming out of the board. Theta hat would actually be for a counterclockwise rotation, but we have negative theta hat, so that it goes the other way. The other thing I need to do is to think about V cross B. And V cross B, think about it, V cross B is going to point in the negative R hat direction. So when I plug these into my force law, I get the charge on this particle, the speed, the magnetic field, and then I have, it points to the center of the circle, so I'm going to get negative R hat. Okay? So that's the formula that you get for the force for a particle moving, and I've written it with polar unit vectors because I know where things are headed, but this is the expression I get. All right. So using this and then setting it equal to F equals ma, I find that the acceleration in the radial direction for a circular path, so that's centripetal acceleration, must equal the force divided by mass. And then it would be minus R hat. And this should have been, this is the formula for the magnitude for centripetal acceleration. It's actually minus V squared times R hat. So equating coefficients tells me that V squared over R must equal QV over M. And rearranging this tells me, well, there are a couple ways you can rewrite this. You could say that the velocity equals R times Q over M, or that the radius equals V times M over Q. Lots of ways you could do this. Okay, so this sort of motion, this spiral motion, is called a cyclotron trajectory. And this kind of idea gets used, and it actually is one of the ways you can identify the charge and mass of different objects or different particles. The idea is, let's say you have a wire that's really hot, and so you kind of know the temperature of a typical particle that might come off of them, off of it. So you could use that to maybe estimate a kinetic energy. And if you know kinetic energy, you might be able to estimate some knowledge about the velocity of the particle. Or you might have there are other ways to do it too, where you can estimate the velocity of the particle. And so what you can visually measure is the size of the arc that the particle makes. So you measure R, and let's say you know the velocity already, and what you can deduce is information about the mass and charge of the particle. What you see is that larger mass particles take larger, swing through larger radii, whereas higher charge particles go through smaller radii. So that's one of the ways, during like in a particle accelerator, they can use the shape and the curvature of the different paths to deduce what's a proton, what's an electron, what's a positron, what's an antiproton, etc. Okay, so those are things I wanted to say about cyclotron paths. Anytime you have a particle moving in a uniform magnetic field, that's what you would get, is these kind of spiral patterns. Okay. Now, so this is the formula for the magnetic force. We also had the formula for the electric force on an observer, a test particle. So if I pull them together, we get the combined electric and magnetic force, and that's called the Lorentz force. So it's a combination of electric and magnetic effects. And the formula is really quite simple. The Lorentz force, the total force, equals the charge of the observer, the test particle that feels the force, the electric field coming from the source. That would just be, if you multiply those, that's just the familiar formula we had. This would be the force on the observer. Plus V cross B. Okay. The force is the charge on the observer times E plus V cross B. And this is just adding together the electric and magnetic forces in a pretty straightforward way. I should have said this. This is the velocity of the observer and the magnetic field from the sources. Okay. Now, one of the, I'll throw out something to think about. If you're riding, let's say you've got an electron in your hand and you're driving down the highway. When you describe the world that you see, sure, you see the highway moving at you, but the electron is sitting still with no velocity. It's just there. So in your world, what you would see has no magnetic effect, it's only electric. On the other hand, the Earth has a magnetic field, so that's enough for us. If somebody was on the side of the road, they would see that the electron in your hand has a velocity, and the Earth's magnetic field is there, and there would be potentially some sort of an electric field, let's say. And so I guess what I'm trying to say is that there's actually truly not a real distinction between electric and magnetic fields, because you can imagine different people or different inertial observers who describe the physics differently. One person in a car might say, oh, no, this electron, if I see it wiggle, it feels a force. Since it has no velocity, I guess, before it wiggles. If there's an electric field, you would say, oh, it feels an electric force only. Whereas the person on the side of the road would probably say, no, it's a combination of electric and magnetic fields. And guess what? You're both right. So that's a little precursor. That's kind of was Einstein's stepping off point to understanding relativity, was the idea that the electric and magnetic fields are different manifestations of the same kind of unified object or unified quantity. Okay, so I wanted to say that. We'll get back to that more. We'll have more on that when we get to light and electromagnetic radiation. But you can already see, if you just think about it, trying to apply this formula to an electron in a car and describe it from two people's points of view, you can see that there has to be some connection between electric and magnetic fields, although it's not clear yet. Okay, the other fact, sort of cleanup fact that I wanted to go through for magnetic fields is to point out that it is an, oh, hold on one second here. Sorry about that. Had a little interruption. I wanted to finish this with an observation about magnetic field lines. Okay, magnetic field lines. It's an experimental fact. I guess we kind of deduce the behavior of the magnetic field lines from experiment. It's a fact that magnetic field lines never cross. They never come together. Never, ever, 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 ever. You might say, how can you have a magnetic field if they never come together? I mean, think about a point charge. Whenever we have a point charge, the field lines start and stop at the same place. They come together. Magnetic field lines never cross. What that means for us is there are no magnetic charges. There are no magnetic charges in the world. You might say, well, if there are no magnetic charges, how can you have field lines? How can you have field lines if they don't start or stop? And the answer is they always form in loops. So a typical situation might be like a bar magnet. Okay, we don't call the ends of it positive and negative, we call it north and south. And what actually happens when you look at the field lines is the following. The field lines form loops which run through the body of the magnet. So the magnetic field lines always make loops and they pass through the body of the magnet. So inside the magnet, they go one way and then they bend around like that. So they always make closed loops. They never actually cross. So there are no magnetic charges or no magnetic monopoles. So that's kind of an interesting observation. It turns out, at least, eventually in quantum field theory, there are some constraints on charges. But when you're studying all the way through quantum electrodynamics, so quantum theory of electricity and magnetism, there's no real obvious reason why this has to be true. And furthermore, so you might think, well, maybe somewhere in the universe there are magnetic charges, just not here. There's actually something called the Dirac quantization condition. And what he was able to show was that if there's one magnetic charge anywhere in the universe, anywhere, then, so that'd be a particle with some sort of charge, we'll call it magnetic charge. It'd be like having a north end of a magnet all by itself with no souths near it. So just a north floating around, say. So if there was a particle, say one of these magnetic monopoles, a north, floating around somewhere in the universe, you can show that electric particles, the electric charges of every other particle must come in integer combinations of some unit. And so it is kind of suggestive that the electric charges of all particles we see aren't just random. They're all fixed integer kind of ratios of some basic unit. And there's no real reason in just quantum electrodynamics, when assuming there are no magnetic monopoles, then there's no real reason for that. And so that is kind of a suggestive thing that perhaps there are magnetic monopoles somewhere in the universe, but experimentally they're not here. In this class, we can always assume that their magnetic field lines never cross and there are no magnetic charges. And if you think about what that means, if there are no magnetic charges, that means that if you try to write down Gauss's law for magnetic fields, it's really, really simple. Gauss's law for magnetic fields, well, remember what Gauss's law said? It said that if I had a region, or sorry, a Gaussian surface, and I computed the flux of field lines leaving the surface, so that the flux counts the net number of lines that leave the surface. If we do this for magnetic fields, that should equal the amount of magnetic charge on the inside. But since there are no magnetic charges, this always is zero. So this says that for any, if you have any closed two-dimensional surface, the integral of B dot dA for any closed surface is zero. So the flux through any closed surface is zero. That doesn't mean that the flux of magnetic field is always zero. It's the flux through a closed surface. So if you had a half, if you had a half of a sphere, then you can have a flux. Or if you had a, I don't know, a cylinder or something like down through the body of a cylinder, that would be okay as long as it's not a closed surface. Okay. All right, so that's what I wanted to discuss in this video. The next video, in the next video, I will talk about the magnetic forces on a current carrying wire. And then let me kind of go through, and then we'll talk about the torque. So it turns out there'll be forces on a wire that carries a current, and then there'll be, if you have a loop of wire carrying a current, you'll get a torque on it. And after we get through that, then we're going to talk about how you actually go about making a magnetic field. Right now, we're still in the part where we're talking about the effects that magnetic fields produce on charges. After we finish that, then we will figure out the how we make magnetic fields. Okay.